The sky hides places where time itself slows down and light cannot escape. You're about to walk to the edge of one of those places and lean over the railing. Start with gravity the way you know it. Drop a ball. It falls. You feel weight because Earth pulls on you and you push on the ground. Now turn the pull up and up again until escape becomes impossible. That is a black hole in one sentence. It's a region where gravity is so strong that nothing can get out once it crosses a boundary called the event horizon. The horizon isn't a wall. It's a one-way door. You can fall in. You can fall in. You cannot come back. How does such a thing form? Most black holes start as the heavy cores of massive stars. A star burns for millions of years, pushing outward with the heat of fusion. When the fuel in the core runs out, the push weakens and gravity wins. The core collapses. If the core is heavy enough, no known pressure can stop the collapse. The star's outer layers blast away as a supernova. The core sinks past the point of no return and becomes a black hole. That's a stellar, mass black hole. There are also giants called supermassive black holes. They live in the centers of galaxies and weigh millions to billions of times the mass of the sun. How they grew so big is a story of mergers, feasting, and time. To picture a black hole, you need a new way to think about gravity. Instead of an invisible force pulling from a distance, imagine space and time as a flexible fabric. Mass bends that fabric. The more mass in one place, the deeper the bend. A black hole is a place where the bend becomes so steep that even light, which always moves at light speed, cannot climb out if it gets too close. That close is the horizon. Outside the horizon, light can still escape. Inside, every path forward leads deeper in. If you fell toward a black hole, you wouldn't feel anything special at the horizon itself. No sound, no flash, just a steady pull that grows as you get closer. If the black hole is small, the pull on your feet would be much stronger than the pull on your head. You'd stretch like a strand of spaghetti. That nickname is silly, but the idea is right. Tides do that. Earth's tides lift and lower the oceans because the moon pulls a little harder on the near side than the far side. Near a small black hole, tides turn brutal. Near a supermassive black hole, the horizon sits so far from the center that tides can be gentle at the edge. You could cross the horizon without noticing and only later meet the worst of it. Matter rarely falls in quietly. Gas swirls and heats as it spirals down. That whirlpool of hot, glowing gas is called an accretion disk. Friction and magnetic fields inside the disk pump energy into the gas. The gas shines in X-rays and sometimes in visible light. In some systems, twisted magnetic fields launch jets out of the poles, narrow beams of fast particles that can travel for thousands of light years. Those jets light up like cosmic searchlights. They mark where a black hole is feeding. We've seen proof from many angles. Stars near the center of our own galaxy loop around a heavy dark object that sits in a tiny space. Track those orbits for years, and you can weigh the unseen mass. The answer points to a supermassive black hole. We've also seen the shadow of a black hole. Radio telescopes linked across Earth acted like one giant dish and imaged a bright ring of light with a dark center. The dark center is not a photograph of the hole itself. It's the silhouette of the horizon against light bent by extreme gravity. The ring is the last traffic of light circling before it's lost. The picture is fuzzy, but the geometry tells the story clearly. Black holes don't only bend paths, they bend time. Imagine you hover far away and watch a clock fall toward the horizon. As the clock gets closer, it ticks slow from your point of view. The light from the clock shifts to redder colors and fades. At the horizon, the clock seems to stop, but that is your view from far away. For the clock, time remains normal. It crosses the horizon and continues on. Two truths coexist because gravity changes the pace of time. That's general relativity working as designed. There's also a limit called the photon sphere, a haunted racetrack for light. If light tries to circle there, the orbit is unstable. A small nudge sends it spiraling in or flying out. Farther out is a radius where stable orbits for matter can exist. Closer in, there are no stable circular orbits. That inner boundary marks where disks tend to end and plunges begin. The exact radii depend on spin. Black holes can spin, dragging space itself around like syrup stirred by a spoon. A fast spin pulls the safe orbit closer to the horizon and can help launch stronger jets. Spin matters for another reason. It means energy is stored in the black hole's rotation. In theory, you can extract some of that energy. Magnetic fields anchored in the disk can tap the spin and drive jets. It's like catching the wind in a turbine built from bent space-time. Evidence supports this picture in many systems. The faster the spin and the stronger the magnetic field, the more powerful the jets tend to be. You might ask what's inside. The honest answer is that our best theory says the center is a place where density and curvature become infinite. We call that a singularity. But that word is a placeholder for our equations break here. Quantum physics should help. But we don't yet have a full theory of quantum gravity. What we do know is enough to map the outside. The horizon is smooth. The region outside hosts disks, jets, light bending, time dilation, and orbits that match math. The inside remains an open book we cannot open. Black holes sometimes come in pairs. When two massive stars live together and both die, each can become a black hole. Over time, they spiral inward. They lose energy by sending ripples of gravity into space. Those ripples are gravitational waves. They travel at light speed and stretch and squeeze space as they pass. We detected those waves for the first time from a pair of black holes merging. The signal was a quick rising chirp. From that chirp, you can read the masses and even the spins. It's remarkable. We listened to the final seconds of a dance that took billions of years to finish. Supermassive black holes also merge when galaxies collide and settle. Their waves are far slower and longer. We can't catch those in a quick chirp with ground-based detectors. Instead, we listen with timing. A set of millisecond pulsars scattered across the sky act like a galaxy-sized detector. Tiny shifts in the arrival times of their pulses reveal a slow, deep hum. That hum is the background song of many supermassive pairs across the universe. It's another sign that black holes shape galaxies not just by gravity near the center, but by the way they merge and grow across time. There's a subtle paradox called the information problem. If you toss a book into a fire, the information about the letters is scrambled but not destroyed. In principle, you could recover it from the smoke and heat if you had impossible patience and perfect instruments. Toss the same book into a black hole and ask where the information went. In the 1970s, Stephen Hawking showed that black holes emit a faint glow when quantum effects near the horizon are considered. That glow is called Hawking radiation. It means black holes can slowly lose mass and, in theory, evaporate over times far longer than the age of the universe for big holes. The radiation seems random, so does the information vanish. Most physicists believe it does not, and that a complete quantum theory will show how information is preserved, perhaps encoded in the outgoing radiation in a way we haven't fully understood. The debate sharpened our understanding of horizons and quantum fields. It's not solved, but the puzzle forced useful ideas to the surface. If you've ever seen a picture of a bright disk with a black center and a hot arc on one side, you've already met another effect. Motion changes light. Gas swoops around the hole at a significant fraction of light speed. Light from the side rotating toward you is boosted. It looks brighter and bluer. Light from the side moving away is dimmed and redder. That asymmetry combined with bending builds the crescent look in many simulations and in the real black hole images. The arc is not a literal flame. It's the side of the disk that motion and gravity make brighter to our view. Black holes also sculpt their neighborhoods. In a galaxy core, gas falls inward and feeds the central hole. When feeding is heavy, the disk glows fiercely. The core becomes an active galactic nucleus. Some of the incoming gas is converted into energy and jets rather than swallowed. Those jets can heat and stir gas far from the center. They can slow star formation by keeping gas too warm to collapse. In that way, a black hole that hides inside a tiny region influences the pace of star birth across a whole galaxy. Observations show a rough link between the mass of the central black hole and the mass of the galaxy's central bulge. Growth is shared history. As the galaxy builds stars, the black hole grows by accretion and mergers. They evolve together, closer to home. Small black holes can quietly glow by feeding on a companion star. Gas pulled from the companion forms a disk and emits X-rays. Those systems flare when the flow changes. They can switch states from dim to bright, from hard X-ray emission to softer light, depending on how the disk is arranged and how hot the inner regions become. Watching those switches teaches us about accretion physics under extreme conditions. You might imagine that black holes vacuum everything nearby. They don't. If the sun were replaced by a black hole with the same mass, Earth would keep the same orbit. It would be dark and cold, but the path would be unchanged. Gravity cares about mass and distance. Black holes become dangerous when you get close, where the curvature is steep and escape speed is high. Far away, they act like any other mass. There's another quiet truth. Black holes are simple on the outside. Their properties are mass, spin, and electric charge. In practice, charge neutralizes quickly in space, so mass and spin carry the story. This simplicity is sometimes called the no-hair idea. All the complicated matter that formed the hole is hidden behind the horizon. Two black holes with the same mass and spin look the same from the outside, regardless of what fell in. We can weigh black holes in several ways. For stellar mass holes in our galaxy, we track the motion of a companion star and use gravity to infer the hidden mass. For supermassive holes, we watch stars or clouds orbit near the center and fit their speeds. We also use the brightness and spectra of accretion disks, though those methods require careful modeling. When mergers occur, gravitational waves give another way in. The signal's shape encodes the masses of the pair and the mass of the final hole. Sometimes black holes help us see the distant universe through a trick called lensing. A heavy mass bends light like a lens. If a black hole passes in front of a background star, it can magnify the star for a short time. On larger scales, clusters of galaxies bend light from galaxies behind them, making arcs in multiple images. Lensing maps unseen mass and gives a handle on dark matter. Black holes are part of that toolkit, even if dark matter itself is not made of black holes. A final myth to sweep away is the idea that nothing ever comes out of a black hole, so we can learn nothing. The horizon is a one-way door, yes, but the effects just outside are rich. Disks, jets, hot spots, flares, light bending, time dilation. All of these leave footprints we can read. Even Hawking radiation, though impossibly faint for big holes, reminds us that horizons are not blank. They are places where quantum fields and gravity shake hands. Imagine the timeline of a single stellar mass black hole. A massive star lives fast and dies young. The core collapses. The hole is born. For a while, it might feed on the star's leftover gas and glow in X-rays. The system settles. If there's a companion, the hole may sip from it in bursts and outbursts. Over millions of years, quiet returns. On rare occasions, it encounters another black hole. They orbit. They spiral inward, shedding energy as waves. In one last second of fury, they merge and ring like a struck bell, sending a clean note across space. That note arrives at Earth as a whisper. Our detectors quiver. We write the event down and give it a name made of letters and numbers. A human century holds that whole story in a few lines of data and a plot on a screen. The universe took 1 billion years to bring the pair together. Now imagine the life of a supermassive black hole. It grows at the hearts of galaxies. When gas is plenty, it eats fast and blazes. When gas is scarce, it dozes. Mergers jolt it awake. It takes in stars, gas clouds, even wandering black holes. It shapes the galaxy's future as it feeds. Over eons, it drifts in step with its home. In the night of a telescope, we see its signature in starlight speeds, and in the glow of its disk, and in the arcs of lensed galaxies beyond. It sits patient and heavy while the galaxy spins around it like a city around a mountain. Stand back and look at what black holes give us. They test gravity in its strongest form. They teach us how matter behaves when heated to extremes. They connect the smallest scales of quantum fields near the horizon with the largest scales of galaxy evolution. They offer clean laboratories in their mergers and wild laboratories in their disks. They are not gaps in knowledge. They are engines for knowledge. Hold one clean picture to end. Far above a quiet galaxy, a thin jet draws a line across space, faint but endless, while at the center a dark circle sits inside a bright ring like an eye that will not blink. Around that ring, gas races and light bends, and time itself runs a beat slower. Nothing breaks the silence there. Nothing disturbs the circle. Yet from that silence, the shape of the universe is traced in light, and the dark heart keeps turning in a place where even daylight learns to curve. The largest structure in the universe looks nothing like a wall or a tower. It looks like frost on glass, a lacework of filaments that stretch for hundreds of millions of light years, and you're living inside one strand of it. Start with the simplest map you can imagine. Put galaxies down as points of light on a dark page. Now back away, patterns appear. The points don't scatter evenly. They form lines and knots in great hollow rooms. Those rooms are cosmic voids. The lines are filaments. The knots are clusters where thousands of galaxies share one deep well of gravity. Thread by thread, knot by knot, that pattern is the cosmic web. Why a web at all? Gravity prefers company. A tiny extra density pulls a little more matter than average. That extra becomes a little bigger, so it pulls even more. Over time, small ripples grow into long ridges and rich nodes, but there's a twist that makes the whole design possible. Most of the mass doing the pulling is invisible. We call it dark matter. It doesn't glow or absorb light. It slips through ordinary matter like a ghost through a crowd. It does have mass, so it bends space and gathers things. Dark matter builds the scaffolding. Gas follows the scaffolding, cools, condenses, and lights up as stars. We don't see the scaffold directly. We see the lanterns hung along it. You can trace the story all the way back to a time when the universe was hot and bright. In that early fire, Tiny ripples in density rode a sea of light. Those ripples left a faint pattern in the oldest light we can see, the cosmic microwave background. Think of it as a baby picture of the universe. The pattern is gentle, the differences are tiny. Over billions of years, those small hills grew. Dark matter, free from the drag of light, slipped ahead and built the first hidden bones of the web. Ordinary gas lagged, cooled, and fell into the waiting arms of gravity. There's a sound locked into that baby picture too. When the universe was young, pressure waves moved through the hot plasma like ripples in a pond after a stone falls in. When the plasma cooled enough for atoms to form, the sound froze in place. Today, if you measure the spacing between galaxies on vast scales, there's a preferred distance baked in by those ancient waves. Astronomers call it the baryon acoustic oscillation scale. It's a mouthful, but the idea is simple. The early universe rang like a bell, and the note left a mark. That mark helps us measure how the universe has expanded with time. Gas that falls into filaments doesn't just sit there. It heats as it compresses and then cools as it radiates. It flows like a slow river toward the knots, the clusters along the way. Gas clouds collide and shock and break. Galaxies form where the gas can shed enough heat to collapse into stars. At first, the stars are metal poor. In astronomy, metals means every element heavier than helium. The first generations forge heavier elements in their cores and in their supernovae. Winds from stars and black holes then blow those freshly minted atoms back out, seeding the web with oxygen and carbon and iron. Later stars and planets inherit that enriched mix. In this way, the web is not a dry scaffold. It's a living loop of fall and feedback. How do we know the web is there if we can't see dark matter? We lean on clever light. One trick is gravitational lensing. Mass bends space, and bent space bends light. So distant galaxies look a little stretched or squeezed when their light passes through a foreground web of mass. Each single stretch is tiny, but if you measure millions of galaxies, average the small shears, and map the patterns, a picture emerges. It's like watching grass bend in a breeze to learn where the wind is strongest. That map traces the mass, not just the light, and it reveals the filaments clearly. Another trick uses the universe itself as a backlight. Distant quasars and galaxies shine with ultraviolet light that crosses long distances. Along the way, that light passes through faint wisps of hydrogen gas that sit in the filaments. Each wisp absorbs a tiny, narrow slice of the light. By the time the beam reaches us, it carries a forest of little bites. Astronomers call this the Lyman alpha forest. Each bite marks a cloud along the line of sight. Stack many sight lines like needles through a sponge, and you can reconstruct the three-dimensional structure of gas across hundreds of millions of light years. You're effectively feeling the web with beams of light. Simulations help too. Take the laws of gravity, hydrodynamics, and expansion. Seed the early universe with the tiny ripples we read from the cosmic microwave background. Let the equations run forward on supercomputers. Out come filaments, knots, and voids. Galaxies ignite along the strands. Clusters grow where threads meet. Feedback from stars and black holes pushes gas back out, warms it, and reshapes the small-scale details. The largest patterns look strikingly like what telescopes see. You can rotate the simulated universe and fly through tunnels as wide as superclusters, then dive into a knot and find hundreds of swirling halos that each host their own galaxies. It's a tour that makes the idea of structure feel physical. Voids deserve their own moment. These are regions where the average density is lower than the cosmic mean. They're not empty, just quiet. Galaxies live there too, but they're lonelier and often smaller. Voids expand faster than average because less gravity holds them back. Their edges, the walls where filaments drape like curtains, are clean laboratories for gravity and dark energy. If you want to test how space stretches today, watch how voids grow and how their boundaries move. The emptiest places can be the best rulers. Dark matter is the quiet architect of all this. So what is it? We know what it does. It clusters. It doesn't interact with light. It moves more slowly than light in the early universe, so it can start to gather before ordinary gas decouples from radiation. The simplest picture is of a new particle or family of particles that only feel gravity and perhaps a weak force we haven't seen directly. There are other ideas, like modifications to gravity at very low accelerations, but the weight of the evidence favors an invisible mass that acts honestly in gravity's game. Experiments deep underground in space and at particle accelerators keep looking for direct signs. None have stood the test yet. The cosmos, though, keeps pointing to the same answer. Something unseen holds the web together. Dark energy is the stranger partner. It isn't a mass that clumps. It's an effect in the fabric of space that drives expansion to accelerate. On the scale of the web, dark energy shows up not as a feature, but as pressure on the whole stage. It pulls distant filaments apart faster than their gravity can draw them together. This competition writes curves in our measurements. Supernova distances, baryon acoustic oscillations, and lensing maps all register the tug of war. The scorecard says, dark energy dominates the energy budget of the universe today. We don't know its nature, only its behavior. The web grows, but it also thins, stretched by an invisible hand. It's easy to imagine the web as static, but everything is in motion. Galaxies stream along filaments into clusters, like cars funneling onto a highway. Clusters merge in slow, thunderous collisions that last 1 billion years. Their dark matter halos pass through each other with little friction. Their gas slams together and shocks, heating to tens of millions of degrees and glowing in X-rays. Sometimes you can see the gas lag behind the dark matter, proving that the two behave differently. The bullet cluster is a famous example. There, the separation between the mass map and the glowing gas marks dark matter's ghostly passage. Inside clusters, galaxies, live rough lives. The hot cluster gas can strip cooler gas from a galaxy that flies through, a process called ram pressure stripping. It looks like a windsock of stars and gas trailing behind a galaxy, a jellyfish shape drifting in deep space. With its gas gone, the galaxy may stop forming new stars and fade to red. On the other hand, tidal interactions in the crowded cluster can trigger starbursts and feed central black holes. The web feeds clusters. Clusters feed back on their galaxies. It's a food chain of gravity and light. Our own home sits on a smaller thread. The Milky Way and Andromeda are the two giant spirals in the local group, a small knot at the meeting of filaments that feed our larger neighborhood, the Laniakea supercluster. That name means immense heaven, and it fits. Streams of galaxies slide toward a central basin called the Great Attractor. The flow is slow on human timescales, yet over hundreds of millions of years it redraws the neighborhood map. If you could fast forward the sky, you'd see entire constellations drift as the local group glides along its strand. Zoom in on a single galaxy. It sits in a dark matter halo, a roughly spherical cloud of invisible mass. The halo shapes the galaxy's rotation curve, which means how fast stars and gas move at different radii. Without dark matter, the outer parts of disks should spin more slowly. They don't. They spin as if held in a giant, unseen grip. Gas rains in along thin tendrils that penetrate the halo. That gas can arrive cold or be warmed by shocks. It settles into a disk, forms stars, and then is stirred and lifted by explosions and by the influence of a central black hole if the galaxy has one. Some of the gas escapes back into the halo as a fountain. Some escapes into intergalactic space. The cycle repeats, fed by the web beyond. The web also sets clocks. The first star, forming halos, were tiny compared to giant clusters. They formed early, lit the cosmic dawn, and bathed the gas between galaxies in ultraviolet light. That light stripped electrons from hydrogen, a process called reionization. The timing of reionization is written into how the Lyman alpha forest looks at high redshift and into subtle stains on the cosmic microwave background. It's also visible in the earliest galaxies we can see with powerful telescopes. Their starlight is young, hot, and blue, and their shapes are clumpy. They live at the intersections of delicate, still forming threads. Neutrinos, those near massless ghost particles, also leave a thumbprint. They move almost at light speed when the universe is young. That speed lets them smear out tiny structures, much like a wind smoothing ripples on a pond. The size of that smoothing depends on the total mass of neutrinos. Lensing maps and galaxy surveys can sense the effect. In that way, the web becomes a weighing scale for particles that pass through your body by the trillions every second without a single nudge. When astronomers measure the web, they worry about bias. Not in people, but in galaxies. Galaxies are tracers of mass, but they aren't perfect tracers. Bright galaxies might live in denser parts of halos. Faint ones might cluster differently. To turn galaxy maps into mass maps, you have to calibrate how light populates halos. Models called halo occupation distributions do this by matching the number of galaxies to the number of halos at different masses. It's a statistical handshake between theory and observation. Do it well, and the map sharpens into a trustworthy portrait of mass. There are practical uses too. The web is the stage for supernovae, gamma ray bursts, and fast radio bursts. Knowing where gas lies along the line of sight helps interpret those flashes. A fast radio burst's dispersion tells you how much free electron gas the pulse crossed. Collect many bursts, add their dispersion measures, and you can count the cosmic baryons, the ordinary matter that used to be missing in our inventories. It turns out a lot of it hides in warm, thin filaments you can't see directly. Bursts make them glow in timing. Even the empty parts teach. In a void, gravity is weaker than average, and dark energy's push is easier to feel. The growth of voids, the speed of galaxies along their walls, and the subtle lensing by their underdensity all speak to the balance of forces in the universe. They are like laboratories built from silence. If gravity behaved differently on large scales than general relativity predicts, voids would be among the first places to say so. It's easy to get lost in the grand sweep, so bring it back to a single feeling. The night sky looks calm. It isn't. Over your head, a river of galaxies flows along a filament so wide it defies immediate sense. At the same time, in a different direction, space thins into a void where a galaxy can drift for eons without a close neighbor. Between these extremes is the everyday of cosmic life, where gas falls, stars form, black holes feed, and then winds and light push back. The tug is never done. The web isn't a picture, it's a slow motion storm. We're still young in this work. New surveys are mapping billions of galaxies. New lensing projects are measuring the shapes of billions more to trace mass. New instruments are capturing faint glows from warm gas that lies between galaxies. Light so dim it was invisible a decade ago. Radio arrays are listening for the whisper of neutral hydrogen spin, flip line from the cosmic dawn. X-ray telescopes are weighing the hot atmospheres of clusters and counting the metals they hold. And deep in the earth, detectors wait for a dark matter particle to tap their crystals or their liquid argon with a single convincing knock. None of these pieces sits alone. Measure the web one way and you cross-check it with another. Disagree, and you've found a problem or a clue. Agree, and your confidence grows that the story is right. The early ripples we see in the baby picture become the filaments we map today. The invisible scaffold we infer from galaxy motions becomes a mass map painted by lensing. The gas we can't image directly reveals itself in quasar absorption lines and burst dispersions. All of it points to the same truth. Structure grew, guided by gravity, on a skeleton we can't see but can weigh. Think of what it means that we sit inside a strand. Our sun orbits the Milky Way. The Milky Way drifts toward Andromeda. Both glide along the local sheet, the flattened layer of nearby galaxies. That sheet itself is woven into a larger filament. The filament leads toward a cluster, and beyond that the flow turns toward a deeper basin. Scale is a ladder you climb by thought. Each step changes what near and far feel like. Yet the rules don't change. Gravity gathers, pressure resists. Light tells the story. It's a humble thought too. The universe didn't build the web for us. It's the simplest outcome of known laws playing out over time. Give matter a little unevenness and the freedom to move. Let gravity do what it always does. Wait. You'll get a pattern that looks like frost, like rivers, like foam. You'll get rooms of quiet and roads of traffic. You'll get cities of light at the intersections. You'll get, at one particular crossroad, a spiral galaxy with a small yellow star and a set of rocky worlds, one of which grows life that can think about all of this. Hold one last image with care. Drift upward in your mind until the Milky Way is a coin on a black table. Rise higher until the table is a wide field and lines of light wind across it. Bright where filaments meet, faint where they trail into open dark. Every dot is a galaxy. Every thread is a drawn-out tide of gravity. Somewhere on one of those threads, a small world turns and listens. Somewhere else, gas slides like mist into a knot where new stars will spark. The web doesn't speak, but it hums with motion. And in that hum, thin and steady, you can feel the shape of everything. There's another layer to the black hole story that sits right at the edge where gas turns into light. Picture a river of matter spiraling inward, thin as a blade and hot as a furnace. That river is the accretion disk. Friction inside the disk, helped by tangled magnetic fields, forces neighboring rings to rub and swap angular momentum. Inner rings lose momentum and fall inward. Outer rings gain some and drift outward. Energy is shed as light. Close to the hole, the gas can reach tens of millions of degrees. It shines in X-rays. The spectrum carries the fingerprints of speed, gravity, and spin. There's a built-in speed limit to how bright accretion can get. If the disk shines too fiercely, its own light pushes back on the infalling gas. Radiation pressure fights gravity. The balance point is called the Eddington limit. Many systems hover near it when they feed well. Some push past it for short times in thick, puffed up slim disks where photons get trapped and dragged inward before they can escape. Others fall far below it. When feeding is lean, the flow can turn into a hot, dilute swirl, where energy stays locked in the gas and slips across the horizon almost unspent. That is a radiatively inefficient flow, a dim, hungry whirlpool that glows more in radio than in X-rays. Spin reaches out from the horizon and leaves a mark on everything nearby, A spinning black hole drags space around with it, an effect called frame dragging. Imagine honey stirred by a spoon. The honey doesn't sit still. It swirls. Near a rotating hole, the very fabric of space swirls. This changes where the innermost stable circular orbit sits. For a disk rotating the same way as the hole, that safe orbit lies closer in. For a disk going the other way, it lies farther out. Closer in means deeper gravity, higher speed, stronger light bending, and a different balance of heat and radiation. By watching how disks brighten and dim and how specific X-ray lines are stretched and skewed, astronomers can estimate spin. One line is especially useful. Iron atoms near the inner disk emit a sharp X-ray line. Close to the hole, that line is dragged to lower energies by gravity and smeared by speed. The result is a broad, skewed line with a long red tail. Fit that shape, and you're fitting geometry. You're measuring how close the luminous gas can orbit before it plunges. That distance depends on spin. It's not a photograph, but it's a clean ruler, and it reminds you that even light carries maps when gravity is strong. Disks don't always sit flat. If the hole spins and the disk is tilted, frame dragging can twist the inner rings and align them with the spin, while the outer disk stays misaligned. The warped shape that results is called the Bardeen-Pedersen effect. Warps can wobble, wobbles can modulate the light. In some systems, the X-ray brightness hums with quasi-periodic oscillations. These hums are not musical notes, but small beat patterns from gas circling and nodding in the warped space-time. The frequencies hide clues to mass and spin because they depend on the deep gravitational potential and on how the disk precesses. Jets deserve a slower look. They are narrow, fast outflows launched from the polar regions. Two main engines likely work together. Magnetic fields anchored in the spinning hole can tap rotational energy and fling plasma outward, a process often called the Blandford-Dusnajek mechanism. Magnetic fields anchored in the disk can also slingshot matter along field lines that open into space, a disk-driven mechanism. Either way, you need ordered fields, fast rotation, and a supply of charged particles. The result is a beam that stays collimated for astonishing distances, sometimes longer than the host galaxy itself. Shocks and magnetic reconnection inside the jet accelerate particles that then radiate from radio up to gamma rays. When a jet points near our line of sight, the light is boosted by motion. The source flares and flickers. We call such beacons blazers. They are black holes with searchlights aimed almost at us. A quieter kind of drama is a tidal disruption event. A star wanders too close to a massive black hole. Tidal forces stretch it into a long stream. The near side of the star feels stronger gravity than the far side. The star unravels. About half the debris swings outward on new paths. The other half falls back and forms a temporary disk. The light rises and fades over months, a flare written by gravity's teeth marks. In some cases, a jet erupts from the chaos. In others, the flare is all you see. These events are laboratories for how matter turns into light when a feast arrives all at once. Not all black holes are giants or stellar leftovers. There may be a middle caste, intermediate, mass black holes heavier than star, born ones but lighter than the monsters in galaxy cores. They're hard to catch because they're few and often quiet. Hints come from unusually bright X-ray sources off to the side of galaxies, from the motions of stars in compact clusters, and from tidal disruptions in small galaxies that seem to need heavier eaters than the usual suspects. If these middleweights are common, they may be the seeds from which supermassive black holes grew. There's an even more speculative branch called primordial black holes. These would have formed in the very early universe from rare overdensities not from stars. Tiny ones would have evaporated by now through Hawking radiation. Heavier ones could still exist. Searches for their lensing effects and for their influence on the cosmic microwave background set strong limits on how many could be around. The idea remains a test case for new physics. It's valuable even when the answer is no. Across the Milky Way, small black holes in binary systems switch personalities as the accretion rate changes. In a low, hard state, the X-ray spectrum is dominated by a hard tail thought to come from hot, tenuous plasma above the disk. Jets tend to be steady and bright in radio. In a high, soft state, the thermal glow of the disk dominates and the jets weaken or vanish. Transitions between states can be fast. They leave tracks on a luminosity hardness diagram that observers learn to read like a weather map. Watching these cycles operate in days or weeks around small holes teaches you physics you can apply to giant holes that evolve in slow motion. Black holes are simple on paper, but the stuff around them makes the sky messy in the best way. Gas clouds drift through the central parsec of our galaxy. Some are shredded, some survive. Stars orbit in eccentric paths, and their pericenter passages test gravity in a regime far stronger than planets ever feel. The starlight redshifts when they dive deep, their orbits precess. Each loop draws an ellipse that rotates a little, a clean stamp of curved space-time. The black hole at the center is quiet today, but the fossil light from past flares echoes in molecular clouds around it. Those echoes, seen as lines that brighten and fade across years, are time-delayed postcards from outbursts a few centuries ago. When black holes merge, the final remnant rings. The ringing is a set of damped vibrations called quasi-normal modes. Think of a struck bell in slow motion, except the bell is space-time itself. The spectrum of modes depends only on mass and spin. Measure several modes, and you test the idea that a black hole really has no hair. That mass and spin tell the whole external story. Deviations would hint at new physics, at structures beyond the horizon, or at alternatives to black holes. So far, within the reach of our ears, the bells sound like the theory promised. The horizon is smooth in general relativity, but ideas in quantum gravity have sparked debates. Does information escape encoded in delicate correlations in the outgoing radiation? Does the horizon bristle with soft hair? Subtle charges that store information. Are there firewalls that break the smoothness for infalling observers? Most physicists bet against firewalls, favoring a picture where no drama occurs at the horizon for someone falling in, while information is still preserved in a way that respects quantum rules. The argument has sharpened our insight even without a final verdict. It's the kind of argument that power washes assumptions and leaves a cleaner set of questions behind. Gravitational lensing by black holes can produce beautiful geometry. Put a black hole between you and a bright background source, and light that would have missed you is bent into view. Perfect alignment would draw a thin circle of light called an Einstein ring. Slight misalignment creates arcs and multiple images. Near a hole, there's a family of photon rings, nested, each made of light that looped the hole an extra time before escaping. Their existence is written into the math of null geodesics, the paths light takes in curved spacetime. Imaging their imprint in the blur of a glowing disk is a task for the sharpest eyes we can build, and each step forward turns a concept into a picture. Polarized light adds another layer. When charged particles spiral in magnetic fields, their light is polarized. Measure that polarization close to a black hole, and you can trace the shape and strength of magnetic fields near the event horizon. Patterns that wrap around the dark center speak of ordered fields capable of launching jets. Changes over time reveal turbulence and reconnection, the sudden snapping and rejoining of field lines that releases energy in bursts. In other words, the darkness has weather. If you could place a clock on the rim of the inner disk and another far away, their disagreement would be a lesson all by itself. The inner clock runs slow. Ticks stretch, signals leaving the deep well climb out redder and drained. Yet from the clock's own point of view, nothing feels wrong. The flow of time is local and honest, even when two observers disagree on its rate. That realization is part of the strange gift black holes give. They force you to separate what is true for one path through space-time from what is true for another, and they make that separation concrete. Even the fate of a lonely black hole has a shape. If it accretes little, it will fade into the background, a dark mass wandering the galaxy, tugging slightly on stars that pass too close, sometimes capturing one and making a quiet X. Ray binary for a while. Over times longer than human language can carry, it will orbit the galactic center, feel gravitational nudges from giant clouds, and perhaps be scattered inward to the crowded core. There, it might merge with others and step up the ladder to heavier weights. The story is slow, but it's still a story. At the other extreme, a ravenous supermassive black hole can set the tempo for an entire galaxy cluster. Its jets heat the cluster's central gas, stirring it and preventing it from cooling too quickly. Without that heating, the gas would condense and form too many stars at the center. With heating, the gas stays hot and buoyant. In X-ray images, you can see cavities, balloon-like pockets carved by jets, rising like bubbles in a pot. The size and number of those bubbles tell you how much energy the black hole has pumped into its surroundings. It's feedback on scales that makes city-sized metaphors break. Black holes also teach restraint. If you stare only at the hole, you miss the orchestra. Stars, gas, dust, fields, and dark matter all play. The hole is a conductor with no baton, setting rhythm by gravity and by the light it helps make, but never playing alone. Each observation adds a section. Spectra lay down the woodwinds. Imaging brings in the strings. Timing strikes the percussion. Polarization, lensing, and waves add the brass. The score is not finished, but the theme is strong. Hold a last, quiet image. In the center of a galaxy, gas curls like smoke around a dark circle that is not a thing but a place beyond return. A few hot knots brighten and fade as they race through the inner rings. Above and below, thin jets pencil lines into the halo and keep going. Farther out, a star clips past. Its light reddened as it dives and brightens again as it climbs. Time runs at 2 paces in the same scene, and both are true. Nothing speaks. Nothing needs to. The curve of light is the sentence. The horizon is the period. And beyond that black punctuation, the universe keeps writing.